Hi, I'm Professor J-Dog, or Justin Hominski, and I'm a student at the University of South Florida studying electrical engineering, and I want to go over an example from Professor Takshi in my Electronics 1 course. So here we're learning about BJTs, Bipolar Junction Transistors, which just means a transistor or a device that switches on and off. It has two modes. We can learn about that more later, but it's just two diodes that are in a configuration back-to-back. Bipolar junction transistor. There's a junction, it's a PNP or an NPN. It's some sort of N and P type dope, but that's more about the physics behind how this works. We want to, in this problem, find V naught. Ooh. Sorry, I drew that earlier. V naught. So, but we can go through that as well. So we're finding V naught here. And if we need V naught, we know that this is equal to VC. This right here in a BJT, this is the VB, this is the VC, and this is the VE. Now, how did I know that? So the emitter is always going to be the one that points the arrow, either in, out. It shows the current flow, but it's always the one with the arrow. It's the emitter. The collector is the one opposite to that one, and then the base is always the one that's shared between the two. So, and if that's confusing, it gets a little bit more, it gets easier once you start practicing with these. So also, if this says RC, this is the resistor at the collector. VC, this is RC, and then the current going through this is going to be, well, you guessed it, IC. Okay, Ohm's law is V, delta V, is equal to I times R, which is the current through some sort of resistive value, gives you a voltage. So essentially these devices have two modes. You have an active mode and a saturation mode. And for this device to be in active mode, your base and this emitter here has to be in active mode, which means it's confusing. Let me rephrase this. To be in active mode, the base to emitter has to be in forward bias, so there's a current flowing through this device here. But this base to collector is going to be in reverse bias, meaning that there's no current flowing this way. It's just through this input loop current. So, and then this voltage here has to be greater than 0.7 volts to overcome that voltage threshold in a diode in order to have current flow through this device. So, I want to give you guys some steps to make it a little easier when you're solving these junctions, these BJTs. And step one is going to be define the input loop. So in our case, our input loop is going to be, we'll go back to these steps as we proceed. Our input loop is going to be the base and the collector here. Okay? Or, I'm sorry, the base and the emitter. So this is going to be this input loop here, this current. So if you see that the emitter is pointing outwards, then that means that current has to flow from the base to emitter, and we have to prove that. So in order to prove that, we're going to draw a Thevenin equivalent model. So if we look at these points here, A and B, the V Thevenin is going to be the 10 volt drop, and then it's going to be a voltage divider. So what's the voltage here at VB? If we have 10 volts starting, and we go through a resistor, right? And then we go through this resistor as well, it's just going to be 10 volts times the 200K divided by 200 plus 200K ohms. It's going to be voltage divider. So if we're trying to find the voltage here, we're going to take the voltage across these devices. This is going to be the 200K ohm resistor divided by the total amount of resistivity. So then this gives us 5 volts. And then we know that we have a resistor in series with that, which is just going to be these two resistors in parallel. And if that's a little confusing, I would touch up on writing Thevenin models. And if you can just convince yourself that this is how you do it, then that works too. But these two are in series, 200K, 200K. And in order to add series combinations, if it's just two devices, you can do product over sum. And that would give you a Thevenin model with 5 volts here, 10K ohms here. And then we're only worried about this base and emitter, BE, because this is our input loop. So once we figured out this, we know that the current has to be positive, or I'm sorry, the voltage has to be greater than 0.7 in order to cross this barrier. If you look here, we can also draw this as a little tiny diode here that we need a voltage greater than 0.7 in order to allow current to flow in the positive direction. So if we have 5 volts here, it's safe to assume we have enough. We have greater than 0.7, and we can say that it's on. So, okay, cool. So now we have to try and solve. So from this input loop, we can do a nice little KVL. So 5 volts, all the volts in this entire circuit, it's going to be 5 volts. We're going to set that equal to 100K ohms times IB, because that's the current times the resistance of this resistor to find the voltage drop. And then we're going to add 0.7. Let me see if I can do a little laser. We're going to add 0.7 to this. And this is going to be due to the voltage across this base to emitter here. So our IB is going to be 0.043 milliamps. Well, once we do this, we figure out, well, what else do we know? We really don't know anything else besides the fact that this equation, we know IB, but we can't figure out VB specifically here. We can't figure out, we really can't figure out anything as of now. So, okay. I think I messed up a little bit on the terminology here. This is going to be 5 volts. This is going to be V Thevenin and not VB. This is VB here, but when we have the VB is going to be kind of down here, and then it's going to still have a resistive value. So we can't actually determine VB. We can't determine VE. We can't determine the voltage at the collector. So what we have to do is make an assumption, assume active mode. And when you're in active mode, the current IC is equal to beta times IB. And in most cases, beta is just 100. So IC is just a factor of 100 of IB, the current of the base. And then, so we can calculate IC as 100 times 0.043, and everything in purple, this is all an assumption. We can't fully prove or say that it's true until we've satisfied a condition. And what's that condition? Our condition is VCE has to be greater than 0.2 volts. Okay? And that's due to the fact that if we look back at this model here, we have 2 diodes along this path here. And in order to have current that flows from the base to emitter, we have to have the collector to emitter be greater than 0.2 volts to overcome those diodes, those threshold diodes. So if we get down here, we find that IC is equal to 4.3 milliamps. So if IC is equal to 4.3 milliamps, which is going to be the current that travels down here, so this is going to be IC. If we found that to be equal to 4.3 milliamps, right, then the voltage at VC, which is equal to V naught, they're the same thing, is going to be the 10 volts, which you're going to start at. Then we're going to minus that voltage drop across this resistor. So if we do 10 minus 4.3 milliamps times 100K ohms, we get negative 420 volts. If VC is negative 420 volts and our VB or our VE is 0 volts and VCE has to be greater than 0.2, then we can't do that. It doesn't work like that. VCE is VC minus VE, and that would be VC, which would equal negative 420 minus 0, which is equal to negative 420. And that's not greater than 0.2 volts, so we cannot say this is true. It's the wrong assumption. But what this allowed us to do is to move on to a factual side of this BJT, that this is going to be in saturation mode. We proved there's only two ways. It's either active or saturation. If you say it's not, if you've proved that it's not active, it's in saturation. So we know that IB times 100K is equal to 4.3 volts, right? We know that. So essentially, we found IB here, and when it's in saturation mode, what's 100% true is VCE is equal to 0.2 volts. And so it makes it a little bit more challenging, but now you have a concrete answer for VCE. So if IB is 0.043 milliamps, like we already calculated, and IE, which is the current in the emitter, is equal to IB plus IC, right? So current in is equal to current out, KCL. Then we can relate these equations. 10 is equal to 100K times IC plus 0.2. So this is going to be this entire sort of loop here. We can take this as 10 volts minus the voltage drop across this 100K ohm resistor, multiplied by the IC, oh, I'm sorry, we'll just do this one first. So 10 volts is equal to 100K times IC, right here, plus 0.2, and that would give us the current, because this is 0 here, so it's this whole flow here, which is IC would be 0.098 milliamps, and then IE would be 0.141 because ICE is equal to 0.2, so that would be the difference there. And then VC, right, would be 10 minus 100K times 0.098, which is essentially what we did here, but just totaled up that VC, which is equal to 0.02, which is equal to V naught. Which would make sense, because if V is 0 volts and the voltage drop across this is 0.2, then our VC is 0.2. Okay, and then we could just find the current there, and that's it. All we're asked to do is find V naught, and you could go through and find everything else now that we've found all the values, but we're just asked to find V naught. So I hope this helped, and if you have any questions, feel free to put them in the comment section. If I spent too much time talking about something, if you want me to go more in depth about things, I'm not really sure. Whatever helps you the most, I can go over more examples, maybe another Thevenin equivalent. If you want me to go over that, I can as well. Let me know in the comments below. Thank you so much for watching. I hope the video wasn't too long. Skip around as you please, and I hope you have a great rest of your day. Thank you so much.